Hello everyone. So welcome to the last tutorial session. Just wait a second. Welcome to the last tutorial session of the impedance course. So today my aim is to just give a brief summary of what we learned as well as complete the nonlinear EIS portion also. And there I'll just discuss in brief about Fromkin Avisudam. So I went through the videos, most of them are theory based. So if I just focus on nonlinear EIS, I won't be able to give a brief summary of what we went through for this last 12 weeks. I think that's also equally important from the exam point of view. So I'll be giving more what to say weightage for I will discuss on linear yes, but mostly on the Fromkin isotherm and some like just a brief idea because all the others are theory. And then someone had asked me about resistance to charge transfer question, so that also I'll be discussing, and Bessel functions. So apart from that, I think it's theory and it's quite most of them are like what to say simulation kind and theory wise. So I'll give less focus on that. And then
Ma'am, I have one question. Please solve assignment number 11, question number 19.
that is the resistance charge transfer. I've done that. That's what I told. I'll discuss
Okay.
on the resistance to charge transfer also. Okay. Yeah. So so those are the things that I'll discuss, and then finally I'll give a summary. So without any delay, we will move on to the uh, class. Since this is the last one, I'll try to cover the maximum. Okay, I hope my slides are visible. I'll just discuss the last portion of that was the assignment 9, I think. Yeah. So in that, in the above, so this was a question where we stopped. Since we finished, we brushed through it very fast. I'll just redo that, or I'll again show you the code, and then after that we'll move on fresh with the today's portion. So this was a question we were dealing with. So it was a porous electrode. So it had the pores in it, and the pore radius length was given, double layer capacitance, conductivity of the solution was also given. We were asked to find out the dimensionless admittance, and after that we were supposed to find out the impedance at 10 hertz. So the real and imaginary part will come. Okay. So the formula is direct. It is the impedance equal to R solution plus the Z pore by N. Okay. So impedance, total impedance of the pore is given by this formula. It has the resistance into the cot H into the dimensionless admittance raised to 1 by 2 by dimensionless admittance raised to 1 by 2. So what I did was I solved using uh, MATLAB. So you have the CDL, that's the double layer capacitance, density, length, radius, frequency is given 10 hertz, omega is given, y CDL, that is nothing but the impedance due to the double layer capacitance, that is j omega CDL. Okay. So sorry, it is the admittance form you have to find out, not the impedance, admittance. And the n number of ports are also given. You know the formula of admittance, which is nothing but square root of admittance into 2i's into square of length into density by uh, radius. You find out the admittance, you find out the mode value of the admittance, then you proceed to finding the solution resistance, and the resistance of the single pore is given by rho into length by pi r square, that's the area. You get that. Then the Z pore, that is the impedance of the total pore, is nothing but resistance of single pore into cot H admittance by admittance. You get the value, and then the total impedance equal to solution resistance plus Z pore by N.
Eh, Excuse me.
Yes, tell me.
In the formula of admittance, we have
Hmm.
written square root, but I think square root is not coming.
I've written it over here. You can see.
But actually, I think square root is not coming.
Square root is coming.
Coming?
Yes. Please. Just wait a second. Give me a second. I'll take my notes.
Ma'am, another point is that is Z4. If we are calculating, then cot H, then
Hmm.
unitless admittance is imaginary, right? So
I
how
didn't
we will
get you.
calculate imaginary only?
Yeah.
Cot
So
H, uh, cot H is there, right?
yeah.
Z4 is R cot H under root lambda divided by under root lambda, right?
Yeah. Yeah.
So if we are calculating this lambda, it comes to be imaginary. Already we calculated in question number 8.
Hmm.
That is imaginary J 0.60261, right?
Yeah.
So how we will calculate imaginary angle, right?
Just
In
wait.
exam.
Okay. Imaginary next time, I'm not sure if you will have to either you can ask in the public that you can ask right to sir itself like can you expect such question because it is difficult to solve it by hand, right? Because like that formula has just wait a second. Let me answer the first question. Yes, this admittance is nothing but the square root of that is dimensionless admittance is nothing but square root of YCDL into rho into L square by R. Okay, 2 into 2 also. So the formula is having root. Okay. So basically, dimensionless admittance raised to square is what is ML. So that's why that root is coming.
Okay.
Please
In
check
my case,
the.
if I do not take square root, then my answer is coming 0.06. That
Yes,
answer is coming.
ma'am, that is only magnitude, I think, right? And if
Yeah,
we are calculating Z total, that is our solution plus
yeah,
Z code divided by N. And
yeah.
Z code we are knowing that is R cot H under root lambda divided by under root lambda, right?
Hmm.
So we
Yeah.
are calculating this, it automatically comes to be because this lambda to the power 1 by 2, it comes to be imaginary and it is in under root. So it's a very difficult to calculate
Ah,
and calculate all this
yeah,
thing.
just wait a second. I was answering the first doubt. I'm not sure how you're getting the same answer in case when you're not putting the root. Because,
Ma'am, there I think not required. Root is not required.
but is might be, I'm not sure on that because this is how the formula is. And if you just wait a second.
You may check in derivations, I think.
No, in derivation, square root is there. So now this is the answer which I am getting 102.1 minus 10.6. Okay. So in case if I remove the square root and again run, I just wanted to see. I'm getting a different answer. Just wait. If you run without the square root, what happens is you will not get the real and imaginary part. I mean, I'm getting a different answer when I'm running with and without the square. So you will have to check
I,
into it.
I, I have got 0.06, which is correct answer as per sir.
Just wait.
This is for question number 8, and that is coming actually imaginary. So they are asking only magnitude, so we are keeping only 0.06.
Yeah. So my
Uh, this directly comes to be right
so
imaginary.
point six
That is
zero
keeping
three six. I'm getting a different answer. There is a small difference in the mod admittance value, but as per the derivation, you need to put the square root because the square derivation says you will get ml, right? Okay, so ml is equal to the just
Yeah, ma'am. Dimensionless admittance required under root. You
yeah.
are correct.
So ml is given as ml square is what is equal to dimensionless constant. Okay, so if you want to find out the dimensionless admittance, you will have to do it like square of ml square. I mean square of ml. Please check into the derivation. Okay.
Correct, ma'am. Because you
Huh.
are not taking here at quote as admittance. It should come under root. Then it's
Yeah.
okay. That is
Okay.
correct.
Okay. So yeah. Next doubt was how to do this question. If in case it comes for the exam, you'll have to ask sir because he is the one who has prepared the questions. So I'm not sure, but you can ask.
I have text to sir, but I don't get any reply.
Sorry.
I have text regarding this to sir.
Yeah, okay. So you have texted in that group,
Yes.
right? So we'll wait for the answer. So this is difficult to do by hand because it consumes a lot of time. So that's why I did it in this. So yeah, so mod admittance, I'm getting this 0.77 value and this the Z total. So real part is 102.12 and imaginary part is minus 10.6. Okay, so that is the first part of my question. Now the next one is the next question is in the above case if solution resistance is 100 ohm which is same as before, find the real and imaginary part at a frequency of 0.1 hertz. So here I am directly changing the frequency to 0.1 hertz and then I am seeing what answer I am getting. So here my answer real part is 102.12 and the imaginary part is 1055.4. In fact, the imaginary value has increased. Okay. So that's the answer I'm getting. This is the imaginary part. Okay. So I finished discussing the this assignment. Now we'll quickly move on to tutorial. Sorry. So this is last week. So we'll just look into. Yeah, so you're moving on to nonlinear EIS. So you know when you're doing impedance, you are changing the amplitude, the perturbation, and you check the impedance. So up to a particular perturbation value, like up to 10 millivolt or 20 millivolt, you will get the same like Nyquist plot. But if you are increasing further, you can see that the behavior totally changes. We say that the nonlinear effect has come to play. So now how to do in those cases when your system shows nonlinear behavior. So that is what is in the next 2 week course. So here the first thing is when we're solving, we will be using the Taylor series expansion or the Bessel function for solving it. Okay, then so you also know that if it is a nonlinear EIS, so if it is linear, I mean our normal EIS, we say that dE by di, that is the differential impedance is what we are measuring. But in a nonlinear system, we cannot say that dE by di is the impedance. So this method will involve a Taylor series or Bessel function or numerical methods for solving. So any equation of the form y equal to 4 plus 3x cube or x to the power anything, it will be nonlinear behavior. And we also learned the Faraday current in nonlinear EIS. We are representing it as EAC naught raised to n at small and moderate EAC naught values. Then we saw that the higher harmonics will come, and there are also cases when the unit of that higher harmonics won't be omega centimeter square. Okay, then we also saw the Bessel functions for your series expansion. All those are being used for solving, and how we'll write it if the n is odd, n is even. So those are the things you saw. Then you came across a two-step mechanism where you saw resistance to charge transfer, etc. Okay, so that was also assignment question, and further you moved on with the Frumkin and Temkin model, etc. So those were the major things you saw in the nonlinear EIS part, right? Now we'll quickly discuss the assignment 11 and 12 question. Okay, just give me a second. Yeah, so yeah, we'll quickly finish this and then move to the next part also. So how to solve? The first one is the Bessel function. Consider the modified Bessel function of the first kind, y equal to I n of x. The value of y at x equal to 0 and n equal to 1 is, okay. So again, I've used the MATLAB code for that. So the x value is given, n value is given. So in MATLAB, the code for finding out the Bessel function is y equal to Bessel I bracket n comma x. The n value is given as 1 in the question and x equal to 0.5. So you have to find the first coefficient. Okay. So when I run that, I am getting 0.2579. Okay. So the answer for this 0.2579, which I am getting. Okay. Now moving on to the next step question. Taylor series expansion for sine 3x is given by anyone?
3 sin x minus 4 sin cube x.
Yeah. So I hope everyone knows how to do this. Okay, you can do it, I guess, because of the time constraint. I'm just moving on. If anyone has any doubt.
The simple Taylor series extension.
Sorry.
Taylor series extension.
Yes.
Whose function fx equal to fx not plus differentiation into x to the power 1 divided by 1 factorial with
Okay. Now the next thing, when EIS is acquired experimentally, it is desirable to apply sinusoidal perturbation and acquire data after some time, because a system response will be steady periodic, noise will be less, both of the above, none of the above. Anyone?
system response will be steady period.
Yeah, so basically it takes some time for the system to give a periodic response. So till then there can be some disturbances, or it might not be periodic, it can be something like this. Okay, this. So if I take something like this, it's possible that the system response might not be periodic for some time before it actually starts being periodic. So always wait for some time and then take the data. So in this region, you see that it is not periodic. So you are waiting for some time so that system response becomes periodic. Now, if this EIS data is required immediately after applying perturbation, data is not KKT compliant. So what this because response violates condition of linearity, stability, causality, all of the above.
This is stability, I think.
Yeah, it is
Already
stability.
this
It is
type of a question asked in previous session.
okay. Yes. So it is not stable. That's why we have it's not KKT complaint. When EIS data is acquired experimentally, it is desirable to acquire data for multiple cycle because a system response will be steady periodic, signal to noise ratio will be better, both of the above, none of the above.
B option, similar to my question, will be
Yes.
better when we are taking
Yes.
multiple cycles.
Yeah. So to overcome to reduce signal to noise ratio, you have to average over multiple cycle, and to obtain a periodic response, you will have to wait for some time. So be clear with that. So for a given system, when perturbation amplitude EAC naught is increased, the nonlinear charge transfer will increase, decrease, can increase or decrease, will remain constant.
Please explain
Hmm?
this question at doubt.
See, there are two terms. When in the charge transfer resistance, you have something over here. B into EAC naught. Okay. And again, you have one term EAC naught here also. So it is a and combined effect of both of them. Okay. So that's why we cannot exactly predict. We'll see the resistance charge transfer. It's the next question, I think. So it is having two terms in numerator as well as denominator. So we cannot exactly say it will increase or decrease. Instead, it can increase or decrease. Okay. For a reaction with one or more intermediates at a given perturbation amplitude, amplitude of oscillation in fractional surface coverage decreases with frequency, increases with frequency, can increase or decrease with frequency, is independent of frequency. So for this, the sir had told in the lecture, it will decrease with the frequency. Okay. A given electrochemical system shows a DC current at a given DC potential. When the AC perturbation is applied, average current under the steady state condition will be same as IDC. True or false? No, it will not be same as IDC. Okay, it will be different. So that's the question we're talking about. So yeah. So here the thing is that question was incomplete. So sir had discussed it that in the poll. I mean the group. So this you have a reaction two-step mechanism. M giving K1. Sorry, M giving a MHO plus electron, and MHO becomes goes into the solution. Okay, so this K2, I think that this should be a mistake. So K1 is there, K2 is there. Kinetic parameter K10 is 5 into 10 to the power minus 10 mole per centimeter square per second, and V1 is 19 volt inverse. K20 is 5 into 10 to the power minus 8 mole per centimeter square per second. EDC is 0.3 volt per OCP. What is the non-linear charge transfer resistance? Can anyone tell me what's the formula first? So the formula is RT inverse equal to, so this was discussed in the lecture. Okay, F into 2 I1 B1 EAC naught by EAC naught K1 DC 1 minus theta SS. So first you have to find out two values. One is K1 DC and theta SS. Please do it and let me know.
Uh, why can't we cancel this ESE note, ESE note?
Sorry, I didn't
When
get
we
you.
get ESE is in numerator as well as in denominator. We can cancel out.
No. This is a Bessel function of B1 EAC naught. This I1 is the Bessel function, the first coefficient. So I1 means n equal to 1 of, so if you saw in this case, so this is how you represent the Bessel function, In of x. So here that n is 1 and x is B1 EAC naught. Okay.
Yeah.
So this is a formula. So first you have to find out K1 DC and theta SS. Please do it. So K1 DC will be nothing but will be K1 0 e to the power B1 EDC. Okay. Now how do you find out theta SS? You will have to do the side balance. So how do you do? Gamma d theta by dt equal to K1 1 minus theta minus K2 theta. At steady state, this will be 0, right? And theta becomes theta SS. This one will be K1 DC, and because K2, because the second step is a chemical reaction and not an electrochemical reaction, this will be a constant. K2 is a constant. It is not dependent on the DC potential. Be careful with that. So this becomes theta SS, and when you rearrange it, you will get K1 DC by K1 DC plus K2 equal to theta SS. So you have the value for this one. You'll have the value. So here K1 DC will be substituted from here. Okay. So you have all the other terms. 2 is there. You have to find the Bessel function K1 DC 1 minus theta SS by ESC naught. Now how do you do it? So I have done that in MATLAB. So that is K1 naught value is 5 into 10 to the power minus 10. B1 is 19 volt inverse. K2 0 is 5 into 10 to the power minus 8. EDC is 0.3 volt is given. F is 96,485. K1 DC is K1 0 into exponential B1 EDC. EAC naught value is given as 10 to the power 10 to the power minus 3, right? 10 millivolt. Okay, so 10 into 10 to the power minus 3, it is given. Theta S is K1 DC by K1 DC plus K2 0, we will find out. Okay, then N value. So it is already given the question that N I1 of B1 EAC naught. So I1, so N is 1. Okay, and X value here is B1 into EAC naught. So we do the Bessel function, we apply, and you see it is RT inverse. RT inverse is this value. So once you find that, you can find out the RT by 1 by RT inverse. So when I solve it, I'll get the answer as 14.49. So my answer is 14.49. 49. That is for this case. Now, next one is for 75 millivolt. So for the same code, I'll just change the value to, here you see, right? EAC naught is 75 millivolt. I'll again run. Answer I'm getting is 11.40. So here the answer is 11.40. So this is how the question has to be done.
But in answer sheet it is given 16 to 17.
Yeah, I also saw that because I'm getting a different answer. But for the same code, I'm just changing the value of EAC naught. The value is coming correctly in the first one. Second one, it's not coming correctly. So as per my assumption, my code is correct. So this is the value it is supposed to be. I'm not sure why it is. Okay. Yeah. So
Value of
this.
K1 DC, what you are getting in the first one, ninth one?
Okay. Okay. Let me check. K1 DC 1.4 into 10 to the power minus 7 for the second part. 75 millivolt. You're asking about which case?
Yes, yes, K1 DC, yes. 1.4 into
10 to
10
the
to the
power
power,
minus 7.
right. Yes, it is right.
Okay. So, yeah, so that's how this problem has to be done. Okay. Now going to the next question. For a given given reaction, impedance under a pure pseudo-galvanostatic mode can be calculated using numerical method. Okay. Now we'll also discuss the next assignment, that is the last assignment, and then I think I've discussed all the assignments. We'll then go for a revision as well as just a brief discussion on the Fromkin isotherm. Okay, yeah. If an electrochemical system is unstable, the effect will manifest in impedance spectra mainly at high frequency, mid frequency, low frequency, all of the above. So basically any of the stability issues will be seen in the low frequency region. Okay. Instability effects in EIS can be identified using what is the technique? We have seen this in the first one also.
KKT.
Yeah, KKT. You can expect so many questions of this form, theory based. So don't skip the first 2 week lectures, you'll have more of such questions. Empirical evidence suggests that direct integration of KKT relation will not flag the EIS acquired under large signal conditions. If current potential relation is exponential, current potential relation is linear, current potential relation is quadratic, current potential relation is sinusoidal.
First to A and B.
Yeah. Next one is in the case of reaction with adsorbed intermediate where the repulsion between the adsorbed species happen, it is best described by Langmuir, Temkin, Fromkin, none of the above. So here, if there is any repulsion, that is actually explained by the Fromkin isotherm. Now, in the case where some of the sites are energetically favorable compared to the others, we can best describe it by, that's for Temkin. So basically what one means is you have adsorption of one species happening and the other one also adsorbs nearby and you see a repulsion between those two species, you can explain by Fromkin. At the same time, you have multiple adsorbed sites. So in the case of Fromkin, it's a repulsion between the species, but all the sites are equally favoring all the species. Here the difference is some sites will be more favorable than the others. So there are high tendency that the molecules will come and approach that favorable sites first. Only once that is filled, the others will be filled that way. In a given system, EIS was acquired at multiple perturbation amplitude and all of them yielded the same data. Therefore, the system response can be considered linear and higher harmonics are negligible. No, that's not the case. That's a false. Even if there is no reaction at a particular condition in the system, second harmonics can arise if the double layer is described by Helmholtz, Gouy-Chapman, Stern model and none of the above. So here the answer is it's Gouy-Chapman and the Stern model. Okay. In non-linear
Stern model, excuse me, Stern model is the combination of both of them, Gouy-Chapman and Helmholtz model.
Yeah.
So actually, it should be Gouy-Chapman model. The answer should be, because Stern is the combination of both.
So doesn't that mean because
if it is Stern model, then Helmholtz model should also be correct because it is combination of both of them.
No, it can be because of the Gouy-Chapman model. So the effective Gouy-Chapman model, right? In the
Yeah, Gouy-Chapman is right, but Stern model, if they are favoring, then why they are rejecting Helmholtz model?
No. In Stern also, you see like most of the molecules. At some region you see the Helmholtz model, and towards the far away from there you see Gouy-Chapman model, right? So that's like the more distributed way. So it can be because of that, right?
Okay.
So that's what my understanding is. So now the next one is in nonlinear EIS, primary response coefficient increases with EAC naught, decreases, can increase or decrease, or is independent of EAC naught. So this is independent. And corrosion current can be obtained using. So here the answer is Tafel and the electrochemical frequency modulation. Standard Tafel extrapolation assumes the contribution of the following to be measured current negligible: solution resistance, double layer capacitance, anodic reaction, cathodic reaction. So the answer is A and B. Okay, solution resistance and double layer it counts for the cathodic reaction and anodic reaction. Okay. So yeah, I think I've discussed the 11th and 12th assignment. Now moving on to, I have one question. Just wait. Yeah, so we'll first start with, or do you want me to do the Frumkin? Okay, we'll discuss the Frumkin model also, and then come to the revision. So this, okay, so I had one more question actually. So that is like a revision. Okay, so before moving on to that, I'll discuss the Frumkin model. So in Frumkin model, so what is the difference? If it was the normal Langmuir isotherm, you have just a fractional coverage. I mean the rate constant is only dependent on the potential you're applying. But when it comes to the case when Frumkin isotherm is considered, you have the rate constant also dependent upon the fractional surface coverage. So that is the difference. So it's a two-step mechanism. M giving M adsorbed plus an electron and this M adsorbed plus, it goes to the solution and you have rate constant K2 and this also an electrochemical step. Both are electrochemical reaction. So if you are writing the side balance, you will get it as dou gamma d theta by dt equal to, both the steps are having the adsorbed intermediate, so it becomes K1 into 1 minus theta minus K2 theta. Okay, now if you are writing the current, you know it is only single electron, so 1 is N F into rate of the reaction. Rate of the reaction is K1 theta, sorry, K1 1 minus theta plus K2 theta. Okay, now when it comes to Fromkin, you have theta, sorry, K is also a function of theta. So what does Fromkin isotherm say? So according to Fromkin, it says equilibrium constant okay, equilibrium constant is dependent, that is the K, dependent exponentially on theta. So this is what is Fromkin isotherm says. So what it says is, if the charged intermediate species, okay, so you have the metal and you have this something adsorbed on it, and if those, that is here M adsorb plus, if these charged intermediate species are repelling each other, then we are giving, if they repel each other, we will give it a, sorry, before that let me write the so the expression is like Ki. So this part is same as before, K1 K, if I am writing it as Ki, you will have Ki naught e exponential Bi into E. Along with that, you will have a term which is beta I into G into theta. So in this way, equilibrium constant is exponentially related to theta, also potential. So what it says is, if a reaction is having a charged intermediates adsorbed on the surface, and if they repel each other, we will give G a positive value. So positive value is given when it is repelling each other. First step, so here if you see, Ki will have what to say, K1 is there, K2 is there. So if I write, K1 will be K1 naught exponential of B1 E into exponential of beta 1 G into theta. Now the next step, it will become K2 equal to same, just the differences, it will be K2 naught exponential B2E. So what happens? In the first step, you'll see the formation of N adsorbed happening. So what happens? The sites are getting filled. Theta value, the sites are getting filled. That is, the theta value keeps on increasing. So because of that, K1 will increase. Okay, so that is what you see. Now, if I am writing the steady state, basically when you write steady state, this value becomes 0. You will have it rearranged, right? And you will have something of this form. K1 naught e to the power B1 EDC at steady state. So this is how you. So in the previous case and all, what you do is you will equate this to 0. So you can expect some numerical problem based on this also. You can write this, you're supposed to find out the theta SS. There can be some possible questions like that also. So, but you see, you cannot equate it and directly find a value for theta SS. Why? Because you have it in the denominator, I mean exponential raised to that also. So, what to say, separation of theta SS might not be possible. You can put different values of theta SS and check for what value of theta SS, the entire equation becomes equal to 0. Now, when you're doing the linearization, there is a again, you have to linearize two exponential term, right? I'm talking about the linearization. There's a linearization. So you have seen already how to do the linearization for this part. It will be nothing but K1 DC, K1 naught, you will take e to the power B1 EDC outside, and then you will do the expansion for exponential B1 EAC. And this part you will write as K1, okay, I'll do that. So along with that, you also have a term exponential of beta 1 G theta SS. So theta can be written as theta SS plus theta dash. Yes. So this one you know how to do, right? This one will be K1 DC. Right? Now what do you do for this? This part, again you can write it as, just wait a second.
Here K1 is equal to K10 e raised to B1, then EDC plus how you have written EAC.
Yeah, this we have already seen in the previous classes, right? When you're linearization, E will be sum of the DC potential plus AC potential.
But in the first step, we have written e to the power
This
e
different.
DC only. Acha, that is different. Acha.
That is the
Okay.
linearization. So this is the linearization step which I'm telling. This was at steady state.
Okay.
So this is the linearization step. At steady state, you don't have AC current, you only have DC. So that's why I am accounting only for that. Okay.
Okay.
Now, just give me a second. I'm sorry, I cannot write like this. Just wait a second. So here if I see, it will be K10 e to the power B1 EDC e to the power B1 EAC. So e to the power B1 EAC is written like this. Now similarly, this part I can write it as e to the power B1G theta SS e to the power B1G theta dash EAC. So if you would have seen the cases still before, the K1 DC is nothing but K1 dot K1 naught e to the power B1 EDC. But here in Fromkin isotherm, this part into this, because potential is also dependent upon the theta. So K1 naught e to the power B1 EDC into exponential of B1 G theta SS is what is K1 DC. You should be careful on that. When it comes to Franken isotherm, K1 DC is no longer K1 naught into e to the power B1 EDC. Along with that, there will be another term exponential B1 G theta SS. Now, whatever left is written. So this part, same way, how I wrote e to the power B1 EAC as 1 plus B1 EAC. Now I'll write this also like that, like 1 plus beta 1. I'll be neglecting all the higher terms. Okay, so this is the equation for K1. So apart from this term, there is an additional term like this. Okay, into this. Okay. Now, same way if I am writing for K2, it will be K2 DC 1 plus B2 G theta dash C plus B2 EAC. So I have written it in the simplified way. How simplified in the sense? I cross multiply 1 plus B1 EAC into 1 plus B1 G theta dash EAC as we multiplied. So what will I get? 1 in a plus 1 B1 G theta dash EAC plus B1 EAC into 1 plus this term into this. So if I multiply this and this, you will have EAC not EAC square. So you know any term with square to the square or higher powers of EAC is neglected, right? So I've just we have to do that. Similarly for K2 I have written. For K2 this will be the simplified form. Okay, I hope that is clear. So now the next aim is to find out theta dash. How do you find theta dash? You have the side balance equation. You'll take this one and you know how you can write d theta by dt as d theta by de into de by dt. Okay, we have seen in many mechanism derivation. So that will become gamma d theta by, sorry, j omega equal to a1 minus k2 into theta, right? Now I'll substitute for k1 and k2. Becomes k1 dc plus beta 1 j theta dash EAC plus B1 EAC one minus theta dash EAC minus theta SS. So that is coming from 1 minus theta. If I substitute theta SS minus theta theta 1 theta SS plus theta dash EAC, if I substitute, I'll get this one. Okay, minus same thing can be written for K2 also. Okay. So you substituted something of this form. Then you will have to simplify, cut out all the terms with EAC. First you will ignore all the term with square to the power EAC or above. Then you will also ignore the constants. Then you will segregate all the terms. You will cut out EAC from either side. You will segregate the terms with theta dash. And finally, if you solve this, you are expected to get something of the form K1 DC B1 minus theta SS minus K2 DC So this is the final expression you're supposed to get. This is the final expression you're supposed to get. Okay. Then after that, what you will do is you will find out IF. So IF, how you will find out? You have the expression K1 into 1 minus theta plus K2 theta. Yeah. Then after this, what you have to do is you'll have to substitute the value for K1, K2, theta. You will have substitute theta SS plus theta dash EAC. You will substitute. Finally, I'm not doing the derivation because of the time limitation. Okay. And you will have to find out the expression of IF as something theta dash. This is the equation you should get. So if you rearrange, you get uh, so you should also know what is the resistance to charge transfer equation if you are applying a Fromkin model. Okay, so please look into this. You have to rearrange it. So this the final admittance equation, and this part is as attributed to the resistance to charge transfer. In case you want to find out the resistance to charge transfer in the Fromkin model, you have to use this equation. Please make a note of that. This RT inverse, not RT, RT inverse. That's RT inverse. So I hope no one has any doubt. Now I'll discuss another question. Yeah. Now I think I've covered most of them. Now we'll go to the revision part just to brief about all what we have learned. Just give me, okay. So we'll start the revision. So before that, I want you all to solve this question. Consider the following circuit given in figure 1, that R3 equal to 1000 ohm, C3 equal to 100 microfarad, R4 equal to 250 ohm. You're supposed to find the value of the element in the equivalent circuit given in 2. That means you have to find out R5, R6 and C6 respectively if you know R3, C3 and R4. How to do? Do you have any idea?
We have to find impedance of both of them, and then we have to compare.
Compare in the sense?
Means whatever the values are given, suppose here we are given R3, then R4, that we have to substitute, and then accordingly we will find
Okay, how do you find?
R5 and R6.
So both
Like
this, like you can tell.
like here 1 upon R4 is equal to 1 upon R4 plus 1 upon R3 plus C3J omega. And like that, we can find impedance from this side. Similarly, we can find impedance on this side also.
But
We can compare them.
R5, R6 and C6 are not known. So compare in the sense, what do you mean? So in the initial classes, we had seen equivalent circuits, if you remember, right? What is an equivalent circuit? So all these four, there are four. So this is one, okay. This is another one, okay. Now there are cases when uh, this case, all these are equivalent circuit, which means if I know values of all the elements of one, I can find this values of all these elements, I can find the value of all these elements and this one, or vice versa. Any of one should be known, I can find all the other three. That's the first point. Next thing is, all these circuits can be used interchangeably. Okay, so instead of that first one, I can replace it with the second one. Still the impedance will be the same, won't change. So if any one of them is given and you are asked to find the other ones, so you will have to find out how. Two conditions. First, we solve it using omega tends to 0. Next, omega tends to infinity. Any question of this kind, this is how you will have to approach your exam. Both using each one of them, you will simplify the circuit and you will find the impedance. So what is the value of the impedance you get when omega tends to 0 over here will be equal to the impedance over here when omega tends to 0. Similarly, the impedance you get over omega tends to infinity here will be same as the omega tends to infinity over here. Okay. So you will get, by doing that, you will get the resistor values. Then you have to find out the capacitor value. The net impedance of the first circuit will be equal to net impedance of the second circuit. You will have to equate and then you will have to find. Are you getting the point? Please start doing. Then we'll discuss. If anyone has any doubt, please let me know. I'll give you a couple of minutes. If anyone has any doubt, please let me know.
R5 is 200 ohm.
R5 is 200 ohm. Just let me check. Yeah, correct. R5 is 200 ohm. What about R6?
It may be 50.
Yes, correct. So now, so that's like, are others able to get? So yeah. So now I'll start doing also. So how to proceed? So what happens when omega tends to 0? Omega tends to 0, that means 1, so impedance over here is 1 by j omega c, right? So omega value is 0. So this will offer infinite resistance. All the current will pass through this, through R4. In this case, all the current will pass through R5 and C6 offers infinite impedance, so R5 plus R6. So first expression is R4 equal to R5 R6. Okay, so R4 value is given in the question as 250 ohm.
250.
Yeah, so this becomes the
R5 plus
equation
R.
1. Yeah, now the next one is omega tends to infinity. When omega tends to infinity, 1 by j omega c offers negligible resistance. R3 and R4 are in parallel. Okay, so the net impedance over here will be R3 R4 by R4 plus R3 because they are in parallel. Now, what about the other side? Other side, R5 is there, C6 offers negligible resistance, so all the current will pass this way. So it is only R5. So I know R3, R4 and everything. So R3 is 1000, R4 is 250. So 1000 into 250 by 1250. So if you solve this, as someone told, it is 200 ohm. Now if I substitute it back here, I'll get R6 as 50 ohm. So this much you're correct. So for any question of this kind, this is how you'll have to proceed. Okay. Now the next thing is you have to find the net impedance. The net impedance you get over here will be equal to this one. Since you know R5, R6 and all, the only variable in the equation will be C6, then you will solve and find. Okay. Now, circuit 1, what is there? What is the impedance over here? Impedance over here is R3 plus 1 by j omega C3, right? Now that is in parallel to R4. Okay, correct? So that I'll write as, so I'm dealing with circuit 1, I'll use a subscript 1. So 1 by, because they are in parallel, I am taking the reciprocal. So here it is R3 plus 1 by j omega C3 because they are in series. Now that is in parallel to this, so we will take the reciprocal. Inverse of that will be the impedance of the first circuit. Now I'm just simplifying it. This 1 by j omega C3, I'll take j omega C3 up. And cross multiplying. Now I'm just cross multiplying and taking the inverse. So finally, I can write the impedance of the first circuit as R4 into R3 j omega C3 plus 1 j omega C3 R4 plus j R3 omega C3 plus 1. So this is the impedance of the first circuit. Now you know what is the value of just wait, give me a second. Yeah, so this is the what you're getting. Okay, first part. Okay, now you have the next equation. I mean next circuit where R5 is in parallel to C6 and R6, right? So how do you proceed over here? Here both of them are in parallel, right? So that will be J1 by C1 by impedance due to capacitor. That will be J omega C6 because it's reciprocal of the impedance. So it is 1 by J omega C6. So it becomes J omega C6 plus 1 by R6. Okay, and you have to take the reciprocal of that. Okay, so that one will be the reciprocal of this one, and that will be added to R5. Are you able to get that? So for just this part, okay, this small part, C6 and R6, if I'm doing this thing, what you'll get? 1 by ZC plus 1 by R6, the whole inverse. Okay, so ZC is 1 by J omega C. So inverse of that again, J omega C6 plus 1 by R6, the whole inverse. So when I solve it, I'm writing over here, I'll get like R6 by J omega C6 R6 plus 1. So this is what I'll get. Okay, and plus R5 because it's in series with the resistor 5. So this is what is the resistor. So you have the
Yes, correct.
so you have the impedance for the first one, you have the impedance for the second one. Now what to do? You will have to equate both of them. Equate both of them by substituting the value also. That is, you have R4 as 250, 1 plus, you have R3 as 1000, J omega into, it's in farads, microfarad, don't forget 10 to the power minus 6 by so here you have other terms also, substitute the value properly. And 50 into C6 at 50 only, right? R6 is 50, we found it out, plus 200. Now what you have to do is simplification, that's it. So now it is pure mathematics which is important. If you do without making a mistake, you will get the value. So if you simplify, if anyone gets the answer, please let me know. I'm writing the simplified version. Anyone got any answer? So you get an expression like this. So you have C6 in the numerator and denominator. So I'm going to cross multiply. Okay. And then simplify it. Anyone wants to try the simplification? Please try it on your own also. Then we'll discuss the answer. Are you able to get something like this? Anyone got any answer? So I can cut off this term and this term. Okay. Now if I rearrange this, I'll get j omega c6 Are you able to get any answer? Are you able to follow the steps which I have written?
Yes.
So finally,
Steps
you
we
will
can follow.
yeah. So finally, the answer is 2.5 millifarad. So you can expect some questions of, see, the thing is you can expect numericals, there will be lengthy numericals also, might be because you have so many theory questions also, so it can be balanced kind. So you can expect anything. So some question will be very simple, you will need only 10-20 seconds to answer. At the same time, you will have questions which you will require 3 to 4 minutes to solve. So practice is what you require to solve. So you can expect such kind of questions. So I hope so. This example which I gave is for this two circuit. It can be any of the four. Okay, any of these four are similarly equivalent circuit. So this is the what you have to follow. First, you will find out omega tends to 0, omega tends to infinity. You will solve and you'll find. Then you'll have to find out the net impedance, equate, and find out the unknown. Okay, so this is how you. This is what you have to follow. Now we'll just yes,
If
tell
this
me.
type of question is asked, then it is good because here no need to remember any formula.
Yeah. So yeah, so even all I think most of the numericals you don't need to learn anything by heart, right? Except the resistance to charge transfer formulas you will have to learn because it's not always feasible to derive and find. If it's something direct, then it becomes easy. Yeah, some questions of this kind will be surely there. I'm expecting such questions. Okay, so now I'll just give a last half an hour. We'll just do a quick revision of what we have seen in the 12 weeks. Okay. So, so you started with the basics of electrode electrolyte interface. Okay. So in electrode electrolyte interface, what all you saw? You started by saying there is an electrode which is immersed into an electrolyte, and what you're actually, when you immerse, what happens is there is a charge separation that is happening. Some positive charge or negative charge from the electrode will align, and because of that, some from the electrolyte also there will be some charge which is getting aligned over here, and there will be another layer of charge again getting aligned there. We called it the Helmholtz double layer plane. You have the inner Helmholtz plane and the outer Helmholtz plane. And we saw that the capacitor value will be around 20 microfarad per centimeter square. Okay, and this one will be happening in a small range of 1 nanometer. So this happens when there is significant concentration of the electrolyte. I mean, there are enough ions in the electrolyte. Then you moved on with the Gouy-Chapman model. So in Gouy-Chapman model, this charge separation happens in the 10 nanometer region, mostly because the solution is less concentrated. So the charge separation happens over a wider range. Then Stern model you saw, which is a combination of inner Helmholtz plane and the outer Helmholtz, double Helmholtz and the Gouy-Chapman model. So that was the next thing you saw. So if the electrolyte is concentrated, all the charge separation will be happening near the electrode, and you can use the Helmholtz model. But also in the case when the solution concentration is very small, something like 1 millimolar, you can go for Gouy-Chapman model. So this one is for something like 1 molar. So you should know which concentration, what is the range in which you see the charge distribution. These terms are important. Okay. Then we came to a case where
Excuse me. So if the solution concentration is low, in that case, which is more
Gouy-Chapman model.
Gouy-Chapman? And
Gouy-Chapman.
if it is high then
High in the sense 1 molar, and other one it is 1 millimolar. Okay. Then you saw the electrode potential measurement. When an electrode is immersed in an electrolyte, what happens is that we cannot measure the single electrode potential, because it forms across the electrode interface there will be a potential drop. So what you're measuring with using the voltmeter is that potential across the electrode interface. Now, then we saw why reference electrode is used. We saw that in different solutions, you immerse it, you apply 1 volt, and you are using reference electrode, it will have same potential drop irrespective of the solution it is immersed in. So whatever is the potential you give, be it 1 volt, then you will see 1 minus x volt over here. If it is 1.5, you will see 1.5 minus 5 minus x volt over here. That means you are able to measure that potential across the electrode interface irrespective of the solution in which it is immersed. It is helpful. So that's why reference electrode is used. Different reference electrodes like AgAgCl, Calamel electrode, HgHgO can all be used as a reference electrode. But what is the problem? Reference electrode is something that should give the same potential drop irrespective of the electrolyte it is immersed in. But if you pass large current, it is possible that you are altering the behavior of the reference electrode. So in that case, what do you need to use? In that case, you have to avoid that large current from passing through the reference electrode. That is why we are using counter electrode. So in a system, you have the working electrode, you have the reference electrode, and you have the counter electrode. The potential is measured between working and reference, and counter and working you have the current passing through. Okay, so that is what you saw here. So in case when solution resistance is too much between working and reference electrode, we saw that there is also a potential drop across a solution in which it is immersed. So in order to reduce that, so to reduce the solution resistance between the working and the reference electrode, what we can do is we can use a lugging capillary. So that will bring the reference electrode closer to the working electrode. Okay, so that also we saw. Then we also saw that the current and counter electrode should have large area, so that whatever
lugging capillary is kept. What is the purpose of that?
You have to minimize the solution resistance between the working and the reference electrode. Because when, see, actually you want to measure, there will be a potential drop at the electrode-electrolyte interface, which we saw over here, right? Now, apart from that, in the solution also there will be a potential drop. So when you are measuring a potential between working and a reference, there are potential drop. You expect something like this, but there will be a small drop in the electrode-electrolyte interface, and another drop will occur across the solution. Okay, so when the distance increases, the solution resistance will increase. So in order to minimize that, we will be using a lugging capillary. Okay, yeah. So then, and we also saw that the counter electrode should have more area so that it can allow large, so that the large current passing, so that we can minimize the current which is provided by the potentiostat. Okay, then we also saw, in order to increase the conductivity of the solution electrolyte, we use supporting electrolyte. Okay, then what did we see? Yeah, then we came to the basics of impedance. So you know, impedance of a resistor will have only a real value. It is given by the resistance R. Now when it comes to capacitor, it is 1 by j omega c. Okay, you should also know over here another relation, that is IAC equal to CdE by dt. You should also know there is a here current leads potential. Okay, when it comes to inductor, it is j omega L, and here EAC equal to L di by dt, and here current lags. So these all you can expect. Yeah, so all this you can expect for 1 mark in the sense MCQ kind questions. Okay, then we also saw that what we are actually measuring is differential impedance DE by DI and not actually E by I. So that is something else. Admittance is inverse. Okay, then we saw questions where we are finding the net impedance and all. In the sense you have what is the net impedance in this case, or so simple questions of this form can come. Okay, so all this you saw in the next week after that. So there also omega tends to 0, omega tends to infinity, you will solve, then the step frequency. From that you will be asked to find the real part, imaginary part, modulus you can take, phase will be tan of imaginary by real. So all those you know. Then you saw how you will represent. It can be by Nyquist plot or it can be by the Bode plot. Nyquist is minus z imaginary versus z real, and Bode is negative frequency versus negative phase. So minus z imaginary versus z real is Nyquist, right? And Bode you can give us minus of phase versus frequency, or it can be modulus of z versus frequency, or it can also be z real and minus z imaginary versus frequency. So these are the things you saw, and there is also a complex plane plot. Okay, so yeah, then after that you came to the types of analyzers. So what exactly equipment is doing, you have seen. So analyzers are of 3 types you saw, 4 types you saw. One is oscilloscope, the oldest one. You give a frequency and it will apply sine wave and the current is obtained. Then lock-in amplifier, there it is important. Lock-in amplifier uses cross correlation technique. So these can come for 1 mark kind of question. And then fast Fourier transform. Then there is also frequency response analyzer. So these are the 4 things you studied. Then you saw what is pseudo galvanostatic and potentiostatic. Why you say it is pseudo galvanostatic or pseudo potentiostatic? Okay, so pseudo galvanostatic mode will be used for corrosion. So such questions can come, where do you use pseudo galvanostatic mode or something like that. You can, it is used for corrosion, biosensors, etc. And here you use it for, sorry, it got mixed up. Potentiostatic is for corrosion and biosensor. Galvanostat is for battery and fuel cell. We also saw battery should be operated in galvanostatic mode, and we saw the reason why. If we do it in potentiostatic mode, the impedance value will be small and the large current needs to be applied. That is not good. So that's why we apply in pseudo galvanostatic mode. Now then we saw different cases. Like at high frequency regime, you see a loop, and we say that that is because of the inductance of the cable and the instrument artifact. So in such case, how we can do is we can use short cables. To overcome this, we can use short cables. So now we also saw that kinetics is seen in mid and low frequency regime. Okay, high frequency will give information about double layer capacitance. Then we saw what is single sign and multi-sign wave. Okay, then also we discussed about non-linear, higher harmonics, etc. So Faraday cage we will be used in order to avoid the disturbances from the environment. Okay, so and current and potential is related in an exponential way. We use that for our derivation and all. Okay, so multi-sign wave we use. Okay, multi-sign means period of combined wave has period corresponding to the wave which is having the larger period when multiple sine waves are given. Okay, and in order to get higher harmonics, what we'll be doing? We need to have more number of point per cycle. For high harmonic. Now for better frequency resolution, we will use long period. We need to have long period. Okay. Then what did we say? We also saw crest factor. Yeah, before that I forgot another important thing. You should know what is RMS. Formula for RMS. Amplitude value, you should know how you find amplitude value. Then you should also know peak to peak. Okay, then we saw what is crest factor. Crest factor is peak value to the RMS value. Okay, then signal to noise ratio of the wave will depend upon the amplitude of the input wave, amplitude of the noise, number of cycle averages, etc. So we also saw about the Schroeder formula there. So these were the things we so if the input waves are harmonic, we will get fewer points per decade, and the input waves are not harmonic, we will have longer acquisition time to reduce the aliasing effect and spectral leakage effect. So these were few of the points which we also saw windowing, etc. in the second week. Then we come to you get an impedance response. We need to know if it is linear, causal, stable, etc. Okay, so what does that mean? Causal means you will be applying a sine wave, you will get the output. So we are saying that the output is only because of the applied input, it has no other noise or anything affecting the data. So that is the first one. Then linear means system can be so repeatability is there, linearity is there, stability is there. Stability means you will apply a perturbation, you will wait for some time, and then if you repeat, then we are assuming that the system should come back to the same state, then it's stable. Okay. So non-linearity, how do you check? We will apply different volt, we will see the plot. After a particular perturbation becomes totally different, we say that the non-linear effects are coming to play. So stability, how do we check? We will do one CAS, after some time we will again, after that immediately we will do another one. If for the same condition we get the same plot, we say that the system is stable. Now the next thing is validation. Validation we can do using KKT. So what is KKT? We say if the system is linear, causal and stable, it will give a coupled response, and their real and imaginary part can be related. So that is what we saw in the KKT. So we also saw that if it is linear, causal and stable, it is KKT compliant. If it is non-linear, it may or may not be KKT compliant. Okay. So if system has a negative impedance, Okay, if your impedance plot has a negative impedance plot, remember KKT will show the mirror image. We had seen all this. So in such case, we should actually treat the data in the admittance form. Similarly, if we have a truncated data, it may show that the data is KKT non-compliant. In actual case, it can be KKT compliant. So either in that case, we should obtain the data over the entire frequency range. Then we came to the measurement model approach. So in that case, we say that if the system can be represented by passive elements, that is R, C and L, then it's always KKT compliant. We saw Voigt element, Maxwell element and the ladder circuit there. So, and in order to analyze the fitting, we will always check the residual. Okay, so residual is Z real exponential minus Z real model by the modulus. So please don't forget to learn that formula. Then we also saw linear KKT. So what does linear KKT do? It is similar to the measurement model approach, but it is posing an additional constraint on RC. Okay, that is how we saw. Then we saw the distinguishability. So based on that only I showed you the one question today. So then after that we saw zero and the poles. So you should know how to calculate the zero and the poles. That is something else you should know. Then you should know. So don't forget to skip this. Don't forget to check all this zero and pole. Then you should know archaic criteria. Okay, this one and AIC corrected. So these are the next things you should know. When N and residual are all given, you should know how to calculate using the formulas. Right? Yes. So up to that were mostly theory. Then you went on with what to say. From week 5 you started the mechanism. So in mechanism, what do you do? The first step is to do the theta balance and the next step is to find out the IF. So theta balance for each intermediate you will write as theta 1, theta 2, etc. Okay. Be careful with the signs and all, do not make a mistake. When you write IF, it will be nothing but NF into rate of reaction, and rate accounts only for the electrochemical step, not for the, that means electron transfer must be there. Please be careful, first identify the electrochemical step and only then write the step. So then after that you will do, so first at steady state you will write. Then after, from that you will find theta SS. Then you will write K1 and K2. Okay, and you will linearize it in form K1 DC1 plus B1 EAC, like that you will write. Then you will substitute for EAC in theta as theta SS plus theta dash EAC. Okay, then your next step is to find out theta dash. How do you do? You will go for the side balance equation. D theta by dt will be represented as theta dash plus d by dt, that is j omega theta dash EAC. Substitute, find out theta dash. Okay, and you will get the final impedance equation. From that, resistance to charge transfer will be Z at omega tends to 0, and polarization resistance will be at infinity. Right? So based on that, you saw for a simple electron transfer reaction, that means with no intermediate, then you saw with one intermediate, and you saw reverse with the reversible step. So the next couple of weeks were mostly based on that, right? With two adsorbed intermediate, etc. Then we came to reaction mechanism analysis challenges. So we said that it is not easy to use because just wait. It's not easy to use. Okay, and it has some limitations, right? You have to look into that. Then you also saw, just wait a second. Yeah, number of parameters in equivalent electric circuit and reaction mechanism analysis. So there is a formula there also, you have to check into that. I couldn't find that in my book now. Right. So then what? Yeah, so for few weeks up to week 8 you were looking into only kinetics limited. Then after that the mass transfer effects also came into account. So that was a case where IF is no longer a function of current, it is IF is no longer a function of potential as here, it is also a function of concentration. So what did you do? If you remember, you treated a potential and different concentrations separately, right? You treated them separately and you differentiated with respect to each of them, like di by dE, then di by Ca, di by Cb, etc., keeping other terms constant, and then you will find it, right? And you solved, so the derivation was solved in the class. So based on that, we had two cases, right? Semi-infinite and the finite equation. So again, there also you should know how to find out RT, RP. Okay, you should know the formula for CAS, CBS. That formula is big enough, you will have to learn that by heart. If you remember, CAS equal to DA CAB by del plus K minus 1 CBB plus DA by DB K minus 1 DC CAB by DA by del plus K1 DC plus DA by DB K minus 1 DC. Similarly, CBS, that is the concentration of B at the surface, is concentration of B at the bulk plus dA by dB, that is the diffusivity, into CAB minus CAS. That's all you will get. Similarly, there you learned the RCT formulae. Then you had ZF formulae also, that is also needs to be by hearted in case if it comes for exam. So in between you had also learned the Levitch, the RD, the boundary layer for thickness, boundary thickness formation calculation formula, that's the Levitch equation, that is a Corticki-Levitch equation, right? So that is also important. That is 1.61 into diffusivity raised to 1 by 3 into omega raised to minus 1 by 2 into kinematic viscosity raised to 1 by 6. So those things, okay. Then you came to CPE behavior. So in CPE, you saw why CPE happens because of the irregularity on the surface. You saw two formulas which again you need to by heart, that's Eumann-Mansfield and the Brugg formula. So both of them can be used to find out the effective capacitance. Okay. So there also you need to know ZCPE equal to 1 by Y naught j omega raised to n. So when n value equal to 1, you can when n value equal to 1, you can say it is behaving like a capacitor. When n value equal to minus 1, you can say it behaves like an inductor. When n value equal to 0.5, it behaves like a complex number. Okay, so those cases you have Eumann-Mansfield, Brugg equation, etc. You will.
If it is 0.5, then what did it? What if it is 0.5?
It will be a complex number. Just telling. Okay. In between that it will be a complex number. That's it.
Okay.
Yeah. Then you have Eumann-Mansfield, the Brugg equation, etc. That's what we saw. Then finally, the nonlinear EIS that we learned today. So in between that, actually I skipped one part. That is for a few minutes I'll just talk. That is the point defect model. So in order to describe the pitting corrosion, it was a model which was told by Digby MacDonald. Okay, it is giving a description of the metal film interface, metal film and the electrolyte interface. So the film will be covering the electrode surface and it is made of a metal oxide. Okay, and it is a lattice, it is not perfect, it will have vacancies in it. So, and it will also have some cation interstitials. So because anions are large in size, we say that those interstitials won't be present in the film. So we saw there are also 7 processes involved. One is cation interstitial generation, where the metal will be going to the film as cation interstitial and a vacancy will be created in a metal and an electron will be released. That was one case. Then cation interstitial consumption was another case where the cation interstitial is diffusing through the film and it reaches the film solution resistance. And it reaches a film. So because of that, there is a solution resistance. And that was another case you saw. Then cation vacancy generation. So cases can be given and you might be asked to identify the case. What is this? So cation vacancy generation is there where you have the movement of the cation from the film to the electrolyte. Okay, so from the film solution interface, and that will result in a cation vacancy in the film. Then you saw the cation vacancy consumption. So there cation vacancy is what is diffusing through the film and it's arriving at the metal film interface where they are getting consumed. So you should know what is an interstitial movement. So it can be either the movement of the interstitial or so if a cation is diffusing from one point A to another point B, okay, and it can happen in multiple step or it can happen in a single step, okay. If in that movement it is getting a vacancy, so once it moves, some cases we feel like the vacancy is getting shifted. So there we say that it's because of the vacancy shifting, vacancy diffusion. And then you also saw the anion vacancy generation, anion vacancy consumption also. So anion vacancy generation means metal atom near the metal film interface. So that will oxidize, it will become a cation. And because of that, what happens? The formation of metal oxide with the anion vacancy will be contributing to the current. So that was another case. Then anion vacancy consumption is the next one. So here the anion vacancy is generated in the metal film interface and that is what will be diffusing through the film and it reaches the film solution interface. So you should know each case. And finally film dissolution. So there metal oxide films will be dissolving at a particular rate and that depends on the solution composition and the film composition. So you should also know the the different models that are employed. You have an electrode and it has an insulating film across it and then you have an electrolyte, okay. What do you say? You will have a capacitive behavior because of the film, then you have the double layer capacitance at the electrode electrolyte interface and finally solution resistance. So you can expect cases where you're given this model or you're described about this case, you will be asked to identify the circuit which will be fitting that. Now you have another electrode and in this case the film is having some porosity. So in that case you will have the because of the porous film you have this entire behavior, okay. So double layer capacitive behavior will be here which is shown over here. Because it is porous there will be some mass transfer effect also playing, so that's why I am giving Warburg also. And there is another resistor and finally R solution. So this is because of the film, okay. And this one I can say it is RT. So now another case is when the film is conducting and moderatively dielectric. So in that case you will see something of this fine. So sir has explained those in the slides. So because of so you can expect such questions also where you are described the model. So this is because of the film and this at the electrode electrolyte interface. So this when the film is conducting. So there are different cases like this. So you should know all of them. So yes, I think I have given the brief summary of almost everything which we were taught, okay, in this 12 week.